Okay, I had a student wonder how to do a problem on queuing theory where you have uh, multiple servers and you have a constant service time and you have arrival time, a constant arrival time. And so I'm at this problem I'm getting out of this book right here. Introduction to Management Science, 15th edition by Anderson, Sweeney, and Williams. It's a very good book for quantitative methods. If you're into that type of information for business management, a very good reference book. So let's just get into this problem and it'll make a little more sense as we go. It says a Florida coastal community experiences population increase during the winter months with seasonal residents arriving from the northern states and Canada. In Texas, they call those winter Texans. I don't know if I think they call them snowbirds sometimes too in Florida. At a local post office, staffing at a local post office is often a state of change during relatively low volume of customers in the summer months and relatively high volume of customers in the winter months. The service rate of a postal clerk is 0.75 customers per minute. So let's put this information in as we read it. So I'm going to go ahead and insert the symbol that the book uses for service rate, which is mu. Okay, and this is service rate. I'll put it behind it. And so it says the service rate is 0.75 customers per minute. Now it's very important to note the unit because the unit is, you have to keep it the same. So if the problem has the arrival rate, this is the rate you can serve. If it has a arrival rate in customers per hour or minutes per, you have to make sure the units are the same. The arrival rate and the service rate have to be the same. So it's out in the same units. So you have to convert the units if they're not the same. Okay, and then it says the post office counter has a maximum of 3 workstations. So K, workstations we usually call K, or you say servers. That's usually a workstation, be like a server. Be 1, 2, or 3, right? And then we want to find. Oh, it also says one more thing. It says the maximum time a customer should wait in the system should be 5 minutes. So we'll use that. We'll call it W because that's what they use for the average wait time in the system, and we'll call that max is 5. We'll just say something like that. Okay, and we want to find and again we should probably label this also minutes. That way we want to keep these units the same. This is customers per minute. This should be minutes. Okay. So we want to find A. Well, they're telling us that in the winter when the snowbirds come down, they think that the arrival rate, and again, I'm going to use the correct symbol for the nomenclature in the book. They think their arrival rate is going to be 1.2 customers per minute. Now, these are the same, so that checks we're good. This is in minutes, this is customers per minute. So it looks like our calculation should be good when we start to calculate because we've got all the units correct. And you want to make sure this isn't minutes per customer either, right? It's got to be customers per minute. Customers per minute. So, because that would be 1 over lambda and 1 over mu. So I'm going to go lambda arrival rate. Just so you guys. All right, so we want to find, they're giving us this and they're saying, what do we recommend? I guess they want to know how many workstations. Something like that. How many workstations do you want? So for solution, well, you know what they have, before we do the solution, let's state part B too. B, we want to know, well, now they're going to say the arrival rate. Let me copy this. In part B, their arrival rate has changed. It's going to grow to 2.1 customers per minute. And I guess we could ask the same questions. How many workstations are we going to need now? Right? And then we're going to make a recommendation. Okay. So for a solution, so the first thing we want to do is we want to calculate this right here. And we want to calculate it for 1, 2, or 3 workstations. So I guess the way we could do it, we could say K, how many workstations we think we might need. And let's go ahead, we want to calculate a ratio here. And this ratio is important because you see it in this formula several times. So it's nice just to go ahead and calculate. And also there's another reason, I'll show you why. So I'm going to insert the symbols again. I'm going to insert lambda, close, and then divided by, well, I don't want that, control, let me try that again. Symbol, lambda. Sometimes you have to hit enter to get out of there because it starts doing some funny things. Divided by mu, enter, enter. And so we're going to go 1, 2, and 3 servers because the maximum is 3, right? And we want to do lambda divided by mu for each one of these. So that's going to be equal to this arrival rate. I'm going to hit F4 because when I copy it down, I want it to still point to that. Divided by mu, F4. So that way if I change these numbers, then this is going to change also. Alright, and now we want to say let me copy this. Lambda divided by mu greater than K. Okay. So that's a question you want to ask. If you're asking a question, a lot of times in Excel you can use something called if. So I'll go equals if this is greater than this. Well, if it is, we'll say yes. If it's not, we'll say no. So it is. Now the reason we're asking that question, if it is, won't work. Maybe we should say yes. This won't work. Okay. And if it's not, then we can proceed, right? So we can't calculate. In other words, our line is going to grow infinitely because our service rate's slower than the arrival rate, right? And we don't have enough servers to cover it. We only have one server. So our service rate is lower now. We only have one server. So this divided by that is, anyway, that should make sense. So that's how you calculate to see. So you can't even, one server, that line will just grow infinitely. And you'll have a lot, it's definitely not going to work here because eventually you're going to run out. Okay, so now we're going to calculate this P sub 0. And P sub 0 is a probability there's no units. And the reason we have to calculate this because it's an intermediate calculation in order to get this W, we have to do this first. And the way we're going to calculate this, it's a little bit tricky. You have to, so it's going to be equal to 1 divided by, and the first thing it says the sum from the n equals 0 to k minus 1 of lambda over mu, which we have that right there, to the n power divided by the n factorial. So I'm going to show you how to do that. So I'm going to put a parentheses first, and then so lambda over mu we already have, right? So I'm going to click on this, right? And then I have to take it to the n power. So I start at n equals 0. So I'm going to take it to the 0 power and divide it by the factorial. That's that little exclamation mark means factorial of 0, because n is 0. I'm starting at 0 and I'm adding all these terms together. Okay, and then so k in this case is 2. So now I have to add another term. So now it's going to be the same thing. This divided by the factorial. Well, now I have to take it to the n is 1, right? And divide it by the factorial 1. So that's my two terms. N starting at 0. I can only go to n equals 1 because k is 2. So 2 minus 1 is 1. So I have n equals 0 and n equals 1. So here's where n equals 0 and here's where n equals 1. Hopefully that makes sense. And then I have to add to that. So now I'm into this part. So I already have this. It's this right here. And I'm going to take it to the k factorial, or to the k exponent. Right? And I'm going to divide it by the factorial of k. Right? So let's just stop right there. I'm going to stop right there for a second. I'm going to move this out of the way so you can see what's going on. All right, so far I've done two terms of the sum term, and this is all in the denominator, so I started it out with a parentheses. And now I have this part here, and I'm going to multiply this times something else, so I'm going to put this in parentheses. And I'm going to take it times, so now I'm into this part right here, k times mu divided by the quantity k times mu minus lambda. So I'm going to do this. So I'm going to do this again, and I'm going to do it in parentheses. And I'm going to go k times mu. I'm going to hit F4 because I want to copy this formula down, right? And I don't want that to move off of that mu. And then divided by parentheses k times, again, times mu, and I'm going to F4 that again because I don't want it to move when I copy it down, minus lambda, right? And lambda is right here. And I'm going to F4 that too because I want it to stick on that. All right, and then I'm going to add another parentheses to close that. And then another parentheses to close the denominator. That should work. All right, so that's a long formula. And so now I got to go down to the next one. And now I have to add another factorial term because now n went up to 2. So I have to go in here. I'm going to go plus this again to the second power divided by factorial 2. So the probability that there's no units in a system if you have k servers is going to be 11.11%. The probability that you have no units in the system, okay, so that's it. It seems like there's an error there. Let me just double check. Why would that be lower? I guess that's true. Okay, that works out. Sometimes things don't look right, but that's right. Okay, and then, so now we have that. Now, let me show you something here. If you don't want to do it that way, those of you that have the book, there's this table right here. in this table, we could look these numbers up. So we have the ratio 1.6. If you go across with 2 servers, it's 0.111, and with 3 servers, it's 0.1. So if I take that to 4 places, it's the same number, right? 0.111, 0.1872. So instead of going through that, if you have the book, you can actually use that, right? So just to show you, you can look those numbers up. I'm going to show you several ways to solve this, but that's one way. All right, then the next thing we want to calculate, again, we have to do some intermediate calculations. We want to calculate L sub Q. Takes a while to get at this because you got to calculate several things in order to get to it. So I'm going to do something called L sub Q. Oop. All right, and L sub Q is lambda divided by mu to the k times lambda times mu. So it's all this, right? So let's just go ahead and put it in here. So it's equal to, we already know lambda divided by mu. We already have it right here. It's equal to this, and it's to the k power, and that's times, sorry, it keeps jogging to the left on me like that, times this, right? I'm going to F4 that because I want to make sure it sticks on that when I copy this formula down. And then times this, F4. And we're going to make sure this is all in the numerator. Right? And I want to divide that by the factorial of k minus 1 times parentheses k times mu F4 minus lambda F4, and then that quantity and that little fraction, we want to take it to the second power. All right, and let's go ahead and put all this into parentheses. So I have the numerator and denominator in parentheses. Let's put the whole fraction in parentheses. And I want to take that times what I previously calculated right here, p sub 0. So you get 2.8444. Let's go ahead and take that to the same amount of places. So this is the average number of units, but this would be people. So the average number of people waiting in line would be 2.844. So if I copy this down, it would be 3.312. Okay, so I'm getting less people because I have another server, right? So they're going to be less annoyed. Okay, so next thing we're going to have to calculate, we have to calculate W sub Q. Remember, our end goal is to get to this W. So W sub Q is this right here. It's the average time someone spends waiting in line, not in the system, but waiting in line. There's a difference between, once we just recently had a presidential election, right? A lot of people had to wait in line. Once you get into the start voting, you're not so upset. But this is just waiting in line. Waiting in the system would be waiting in line and voting, right? But W sub Q is just waiting in line before you vote. All right, so let's say, so that's going to be L sub Q divided by lambda. So that's an easy calculation. It's just going to be equal to this divided by lambda, but we want to make sure we F4 the lambda again, because when I copy it down, I want to make sure it's still pointing at that lambda, right? And let's go ahead and format those to 4 places also. So this is the average time. Remember now, what is the units on this? Well, we used minutes here, so these are going to be minutes, right? So now we're finally ready to calculate W. And W is going to be calculated using this formula. The average time a unit spends in the system, and W is going to be equal to W sub Q. This new mouse I have likes to jog to the right. It's kind of fancy. So W sub Q equals, I'm sorry, W equals W sub Q plus 1 divided by mu. And if I F4 that, and remember this is minutes, right? So, and then finally we could say equals, I'm going to make it like this, equals is my cap locks is on, I think, is W less than or equal to, and I'm going to click on this and F4 it, and question mark. Forgot to put the question mark into quotation mark. So is W less than or equal to 5? And I can go equals if this is less than or equal to this, F4, value of true, yes, value of false, no. Close the parenthesis. So you're going to use the least amount of servers, so your answer would be use this right here. Okay. So we want to make sure that this is less than 5 minutes, right? Because that's what they said. They said up here maximum time. They should say maximum average time, right? We're using the average time, the maximum average time. So that's part A. Let me insert. This is a solution to part A. So for part B, well, we could copy this down and adjust it. This is the beauty of Excel. Now these are going to be pointing to this, right? And let's go ahead and add one. Let's add one. We'll make this 4. We might need more than 3. So let's go ahead and just copy this down. I'm going to get rid of this yellow because we don't know yet how many servers we need because our arrival rate has changed. But we got to make sure this is equal to that divided by that. And then we'll copy that down. It's going to be 2.8. So now we know 2 servers won't even work. So I'm going to go ahead and get rid of these because our line is going to grow infinitely. So we know we need 3 or 4. But we have to change this because these are all, no, this is why it's so nice to do this. So these are all pointing to this. All I have to do is just drag anywhere it's pointing to that, I just drag that down, right? And I go here, anywhere that's pointing to that, I drag it down. Drag it down. And go here. You want to drag that down. Go here. That's okay. Alright, so now we have, so we basically right away, we recalculated this and just moved everything that was pointed to that, right? And everything else is the same up above. So now this one is 4 servers, so I need to add another term in here. So I'll go plus this to, remember we're going to the k minus 1, so now it's to the 3rd power, divided by factorial 3. Okay, Just let me make sure that's right. Something seems... Oh, you know what? Let's drag this down. You know what I forgot to do? I forgot to drag all these down. And then I change it. I knew something was funny. Okay, plus this to the third power divided by factorial 3. Okay, that looks better. All right, so we see right now that we would need that many servers, right? Now again, you could look these up. These piece of zeros, you could have looked them up too. Like this is 2.8 now, so this is 0.160, this is 0.50521, right? So this looks different, right? 0.0502. That's a typo. That should be 0.05021. We take this out. So that's why sometimes using tables, that's a typo, isn't it? We have the exact answer is right here. It should be 0.502, not 0.0521. So that's why sometimes it's better to calculate things out exactly. But anyway, I just noticed that right now. So anyway, so we know that we need 4 servers. So my recommendation would be we need to expand the number of workstations to 4 in. And what do they say? This is going to be in 2 years. Well, we just say 4. We don't know when it is. Let them decide when they want to do it. But in order to meet that requirement of 5 minutes or less, you need to expand the number of workstations to 4. Now, so I'm going to make this video a little bit longer. This is probably all you need, but I'm going to show you one more. I'm going to show you a really quick way to solve this. So, if you hear my class, in my quantitative methods class, and you go to our course, and you download this zip file, and go to chapter 11. Go to chapter 11, Excel files, and we want multiple. If you open that up, enable editing, enable content. Well, you can change the servers here. So let me make this, let me make it a little bit smaller so you can see what's going on. And I'll compare it with the other one. So we're working on, if we work on this bottom one, I could say, well, if I use solver, so I can go to data, I go to solver, and with solver I can say I want to set this W to a value of 5, because that's my average wait time, my maximum average wait time. And then what I want to change is I want to change this number of servers. And if I go solve, you can see that it changed the number of servers to, oh, you know what, I forgot to change some things. The arrival rate is 1.5, and the service rate is 0.75. No, in this case it was, what was it, 2.1? The service rate, the arrival rate is 2.1, and the service rate is 0.75. So let's try it again. Solve. Okay, so what happened here? Let me change this to something that makes sense first. I'll put it to 3, solve. And it says you need 3.09 servers. Well, I can't have a fractional server, so I change that to 4. and I get the same numbers I have right here, 0.0502, 1.002. So I could go plug in these numbers. I could change these and then plug in 1 server, 2 server, 3 server, 4 server, and note this W, and I don't have to go through all this work. So so if you have the textbook, if you're taking my class, you have this file available. All right. So I've showed you multiple ways to solve this thing. Hopefully it kind of makes sense. Remember, this is for a MMK model. MMK, where you have exponential, you have Poisson arrivals, and exponential service. And K is multiple servers. This model simplifies if you only have one. Actually, you could use this and just if you put 1 in here, it still calculates it. But in this case, it won't, because because of this problem here, where mu divided by lambda is greater than K. So anyway, my picture is going to come up here. I know this is kind of a long video, but my picture is going to come up here. If you like it, click on my picture, and that'll subscribe you to my channel. Also, if you'd like it, do a thumbs up, right? I would appreciate it. Encourage me to do more. Make any comments you want to. So thanks for watching.